I'll share the screen. Yes. Yeah. So let us review what we did the last time, right? Not review in the sense that just review the definition of connectivity. I mean, connected, not connectivity of connected spaces, right? So let us quickly do that, because this is the new concept which we saw the last time. Review of, and just give me one more second. I have to. Okay, yeah. Review of definition of connected space. Definition of connected space. Well, I should maybe just say connected set, but obviously these sets are not just sets. They have a notion of distance in them, for which we are currently doing it. And even not just any notion of distance, but we are just doing it on R and R2 and R and R2 basically. Yeah, a set which is basically just, okay, someone has joined. Okay. Okay. Basically just a subset, right? Subset of R or of R2, right? So we had made a definition. Now, obviously today, I'm just going to restate the definition and also state it in other different form, give other formulations of it and not try to motivate it and so on, because we've already done that. Okay. So the number one definition was that a set or a subset of R, subset of the reals or of R2 is connected, okay, if it cannot be, okay, cannot be written as a union of two disjoint open sets. Okay, everybody remembers this definition? Yeah, something that cannot be broken up, right? But here it means that something that cannot be written as a union of two disjoint open sets. Okay, open sets, we know what that means. So I would ask if someone can give me another definition, an equivalent version of this, another version of this. So maybe I'll just say version 1, version 2. They're obviously all equivalent. We don't have to do a rigorous proof of that right now, but because in different situations, you see, you'll have to maybe one version may be more suitable than the other to prove that something is connected. So can anybody give me another version? In fact, that version is a more intuitive one. There are many versions, but okay, by the way, can you guys hear any noise? Is it coming to you people? Yes, yes. Ha. Okay, let me just close the door and see. 1 second. Okay. We usually keep our doors open in the house. So yeah. Anyways, so this is version 2. Now let us see if anyone, and I had described this the last time, but I didn't state it clearly. Let's see if someone has cooked it up or read about it or anything. So what is the more intuitive definition, or what should be a more intuitive definition of a connected set, a subset of reals which is connected like an interval? Okay, so so let me see, and let me say, and then you guys will surely be able to relate to it. Okay, I'll ask. Let's see. So once again, it means basically that it cannot be, just to say it briefly, cannot be. So let me say it more clearly, because this is the first time I'm defining it, but not too verbally, but still just mathematically, I'll say it. Do is S a subset of R2, or doesn't matter. Let's say R2 is connected, okay, if S cannot be written, let me just say it absolutely clearly, S cannot be written. We want to make the subject feel very natural, so we just want to say that all these things are very naturally similar and some of them have the advantages over the other and stuff. Cannot be written as a union, A union B equals to S. This cannot be done. Okay. Such that, okay, obviously this can be done only if this is the condition, but such that A intersection B is empty. Okay, so obviously, so such that these are disjoint, and now this can also obviously be done. Set theoretically, you can make them disjoint, but what else do we want two connected sets to be? I mean, it's not just that you cannot break them up set theoretically, but the other condition is that the limit points of A, meaning the limits of A, those points, which are limits of sequences in A, roughly speaking, okay, limit points of those points which are those points which are not in A but are arbitrarily close to A, let's say, okay. So the limit points of A intersection B is empty. And obviously symmetrically limit points of B has nothing to do with A. Okay. So it is not just that A and B are set theoretically disjoint, but they are topologically, or maybe that word is not yet premature, but they are disjoint even in a more stronger sense of analysis, where the limit points also are not, limit points of A are also, not in B, vice versa. Okay. So today I've given a formal definition. Okay, this is the formal definition of version 2. So does everybody roughly see why version 1 and version 2 are similar? Roughly. You can just replace this by can. So if a set can be written as a union of two disjoint sets, then show that, yeah, as a two open sets, then yeah. So let's just see, like if there is a set, or if there is a set which can be written, so maybe there is this set, but maybe this is a set, right? If it can be written as the union of two open things, right? These are open sets. This is the S. This is the big thing is S. Yeah. And if these two are the parts of S, and these two are open, then you can understand, right? If this is A and this is B, and maybe this is all S is, if it can be written as union of two disjoint open sets, then obviously, right? Any point you take which is in B, let's say, this cannot be a limit point of anything in A, right? Because you can draw a small neighborhood which is inside B. It has nothing to do with A, because B is open. Okay. And so that point cannot be a limit point of A, and vice versa, and so on. Okay, so this is rough intuition. Please prove this rigorously. Write it out. Okay. Show, you can even show it to me, send it to me. That will be good. So show that version 1 and version 2 are equivalent. It's almost very clear, but please write it. Okay. It's never a bad idea to, because when you write it, you may see it in your own way. You may see something which I've not said, and so on. So this is, higher maths is a bit more about, stating things in the right way, making the right definitions and so on. Yeah. And version 2 is obviously very good for various purposes. It can be defined with less, using less things. It's just as the joint open sets, roughly speaking. Later on, we'll see why more as to why it's a better definition, but for now, they are the same definitions theoretically. Okay, so that was the first small thing. Please show this, please write this out, okay? Don't let them, if you keep writing this, then you'll be better, you know, you'll enjoy the subject more. Yeah, so, okay. So these are the two definitions, and the third thing I wanted to do is I wanted to give another definition, yet another definition. And all these can be useful because the set that you might be presented with, let's say subset of R2, you know, it may not be amenable to these two definitions. Yeah, let's just take one more definition. Let's just take one more definition. Okay, but before that, I want to introduce some terminology. Some terminology for another definition. Okay, so let's start with a set. Okay, start with a set A in S, which is in R2. Okay, so you have R2 and then you have S, and inside you have A. Okay, now A may not contain some of its limit points. Yeah, so there are two cases arise, right? Whenever you look at a set, whenever you look at a subset A of a set S, okay, so S is like our universe now. Okay, it's not R2, but just I'm just saying because we are inside R2 all the time, but S is our universe. Inside that we have taken a set A. Okay, I've taken a set A. Now when you take a set A and you want to do analysis on it, you want to do geometry on it, right? And you'll be looking at sequences in A, right? You'll be looking at sequences in A and so on. What would you ideally want, right? For a complete theory, you would want the sequences in A, okay? Say there is a sequence, so this is A. You would want the sequences in A to have the limits in A, right? But that may not be the case a priori, right? So that's what I'm saying, that there will be two possibilities, okay? A may have all its limit points, and obviously the second case is A may not. Okay? A may not have, yeah, A may not have all its limit points, may not have some of its limit points. Let's just say it like that. May not have some of its limit points, right? So what we try to do is we take A and we add to it the limit points of A. Again, what are limit points again? Just the limits of all possible sequences in A. Simply put, okay? Simply put, it is the limit, the possible limits if you run over all possible sequences in A. Okay, so we take A and we attach to it all the limit points of A. So it's basically like attaching the boundary of A in some sense, right? That's why you see I've drawn a dotted one. So now when you close it, it becomes like this. This is what we tend to do, right? And this is called, this is not a very good definition, but the CRISPR definition might not seem very intuitive to start. Okay, but for the time being, I think it's the same. And this is called the closure, not a bad name, right? Closure of A. Okay, we're making it closed, a closed system. Okay, so there's nothing outside that is on its boundary. It contains its boundary now. It's a closed, so it's a closed thing. Okay. Yeah. So now A bar is a set which now contains all its limit points. Let me give that as an exercise that is not totally trivial. Okay, but give that as an exercise, so you should try to prove it. Yeah. By the way, this is metric spaces. If meaning that we have to do some metric spaces to move forward in complex analysis. Okay, so usually the sources I know of usually will do metric spaces in more generality. Okay, so no, sorry, so no need to read that. You can refer to Patil and Sherbet. I think he will, he obviously, yeah. So Bartlett and Sherbet will have, just look at the right chapter. I think you obviously find it, okay? Because if you go to read metric spaces from some metric space book, you may not like it in the beginning because they do it for an arbitrary space with just the bare minimum properties of distance and so on. So leave that maybe for the time. If you're comfortable, then you can read, but Bartlett and Sherbet is what I will recommend if you want to look up these definitions and so on, okay? But obviously, these exercises that I'm giving, if you also just do them, that will be very solid, maybe build solid. Bartlett and Sherbet, for metric spaces, there are books like Shirali. There is a book by Shirali, Satish Shirali, I think, something. Shirali Metric Spaces is a good book, but it's pretty abstract, okay? So I do not recommending this, but you can check it out if you want. I have read parts of this book. I think I've read most of this book. I liked it, so that's why. Otherwise, obviously, there are the whole hundreds of books on these topics, but these are the books that I liked. Okay, so Bartlett and Sherbet I didn't like so much, but it's a good book. It's okay. It's a very good. It's a nice book. Okay, but Shirali's book is really good. Okay, so you can note it down, and if you want. Okay, so now you see, now the claim is, and I will not prove this, try to prove this is easy. Claim is that A bar contains all its limit points. Okay, yeah, just try to prove that. And these sets which contain all their limit points, okay, sets that contain all their limit points, means there is no limit points outside. All their limit points are called closed subsets. Some of you may know this already. There are only 2 of you now, but called closed subsets. Yeah. Okay, so what are some examples? Obviously, like a closed interval you can take. Yeah, anything outside is obviously outside. It's completely outside, right? Anything outside is not a limit point. It's not the limit of any sequence because you can just make a neighborhood. Yeah, so anything closed subsets are basically sets that arise out of a closure of sets, arise out of equations of polynomials, inverse images of points under continuous functions. Any finite subset will be closed and so on, but we don't want to go into the whole theory of it right now. This is all we need. Okay, any doubts so far? No? Okay, so please prove this. Okay, please prove this is, you may think this is just trivial, no, but just think about it. Okay, write it, and you might see there is something that you have to still prove. Prove this. Now, I just did what was necessary for us to come to the next definition of thing. You see, why am I doing all this? A and its limit points of A? Because see, one of the definitions was, right, that the limit points of A has nothing to do with B. The version 2, okay? So reframe version 2 in terms of closed subsets. Yeah, what did we say? That the limit points of A doesn't have anything to do with B, but it's fine. But the limit points of A along with A also have nothing to do with B. This is what we said, right? Yeah. And we also said that the limit points of B have nothing to do with A. B along with its limit points, those which are in S. I mean, yeah, obviously because A is in S, so that doesn't really make much sense. Yeah, okay. So what does it mean? Okay, it means that, it basically means that A and B are closed in S. You see, because let me just say, it's if you have this set S, and if you have broken it up like this, and this is your A and this is your B, and you're saying that A has limit points, but A has obviously a limit point. Some of it may be in A itself, some of it may be outside A. But if it is outside A, then it is outside S. And those which are outside S, they don't exist for us. Just forget about them. Okay, so any limit point of A is in A only, is not in B. Outside S, we don't care about that. We are interested in S. Okay, so in S, A is closed. If S is your world, then A is closed and B is also closed. Okay, that's all I'll say. Now just reframe this definition using closed subsets. Okay, so basically it will be like write it as a union of disjoint closed sets. Okay, so those open sets are actually closed sets also. So that's the thing. But just take your time, write out all the definitions, or just look at this again, and just think about it and write it out. Please write to work, spend time and write these things. Okay, higher maths is about problem solving also, but it's also about, you know, basically building the right language. Okay, first, so you have to spend time in this definition and so on. Okay, so far so good. Just give me 1 second. I'll just drink some water. Next, I will just come to one point which I might have be confusing all the time. So I will just say it 1 second. So I want to just clarify the notion of 1 minute. Yeah, let me just say it from here only, from the very okay. So I want to clarify the notion of this thing, neighborhood, you know, because this may have confusing neighborhood in a space versus neighborhood in a subspace. You see, all these things that we are doing, you know, but it's interesting in its own right to play around with the definitions and prove interesting properties, see if with less assumptions you can prove and so on. Mathematically, it's interesting by its own. But if you don't find that interesting, maybe, then you can understand that we are just setting up the language. Okay, we are setting up the language to explain the things that we see or that we intuitively believe should be correct. And so that's what we are trying to do. Okay, and all these will come to good use. You will see when the theorems come, then you see, okay, this why that space, that subset should have been connected. But you may not say connected if you don't know the language, right? And then you may say something, some long sentence. And then you may not know properties about sets of that kind, but if you isolate it, make the definitions, work on them, prove theorems about them, then you can use. So it's a language that we are making to do things, okay? But as you can see, it's interesting in its own word, okay? So this point about neighborhood in a space versus neighborhood in a subspace. So what do I mean here? Okay. So yeah, let's take it very basic. So if we just on the real line, okay, let's say you take this, okay. Now, if you take -1, 1, okay, -1, 1, okay, is open neighborhood in R, obviously. Now, if I take a subset, if I take a subset S equal to, let's say, -12, infinity, okay, then the question now is that is -12, 1 open, is -12, 1 open? Okay, so this is not a well-defined question. When you say open, you have to say open where. Okay, if you ask is -12, 1 open in R, then obviously the answer is no. Yeah, that is obviously I'm not writing it. Okay? -12, 1 is not open in R. Okay, because we know the definition, right? At every point, you must be able to draw a neighborhood, so on. Okay, but question is it open in S? Okay, and the answer is yes. Okay, and this is more, it is more than anything, it is mostly by definition. I'll say what the definition is. Okay, but let us just take a minute, take a second and think about this. Why is it okay to call that this is open in S? Yeah. So in some sense, you see this, if you say this is not open in S, and then it's more like, it's more because of the deficiency of the space that you are not calling it open, right? It's more because of the deficiency of S that you are not calling -12, 1 open, right? But that doesn't make sense. Yeah, -12, 1 is as far as it can go, right? It is yeah, it is as far as you can go. Yeah, basically that's all I'll say. So it's okay to call this open, okay? But by definition, so should we say like that, or? Yeah, but by definition, the open sets, by definition, open sets of S are open sets in R intersection with S. So you take open sets in R and you just take their intersections with S, and the things that you get will be by definition open sets in S. Okay, those are the things that we declare to be open in S. Okay, those are the intervals in S, and that's not bad because, well, initially we only defined open sets for R. We didn't define open sets for a subset. So we just, what we are making is a definition, and there was no previous definition or previous, way to understand what open sets are rigorously in S. Intuitively, maybe it's okay. So, sorry, yeah, 1 minute. Yeah, so it is fine, right? It is fine to call it so. That's the thing. So when you want to understand open sets of a subspace, then S as a subspace of R is a subspace of R, right? So to understand what is an open set in S, it should just be cut out by an open set of R by S. Okay. So this is just a small thing I should clarify so that we can move forward. Okay. So let's move on. So we had some unfinished work last time that was connected sets of R, the simplest, the first things, yeah, connected sets of R of the reals. Yeah. So the claim, we knew what the claim was, and I had asked you guys to complete it. I suppose you should have tried. You would have tried. Let's see. Okay. So this is the claim. Claim was that intervals that could be open, closed, half open, half closed. Intervals are the only, there's no other, the only connected subsets. So should we complete the proof of this? Okay. So let us start with, I think let us start with the easier direction. Yeah. Let S be, let's see, I don't know which one is this. Let S be connected. Okay. 1 second now. Yes. So let S be connected as a subset of R. What is it that we want to say? We want to show that S is an interval. How do we do this? Anyone? We just want to show that S is an interval. This is the easier direction, I think. Yes, I think he was traveling, so he was having some network problems from the very start, he told me. But yeah, so let's do it. Either ways, one other person, I think there was some timing confusion. So either ways, we'll complete it. I'll send the recording later on. Okay. Yeah. So let's try to show that this is an interval. Okay. So this is a very intuitively, this is the correct statement, but yeah. So why can nothing else be connected? Why should it have to be an interval? Yeah. So we have to go to the definition of an interval, okay? And obviously S is non-empty, and also S has at least, so yeah, I must maybe say that, maybe no, I don't need to say that, because a single point is also an interval, okay? So if it's a single point, then there's nothing to do, right? So let's just write the proof clearly. Assume S has at least 2 points, X and Y. Let's say X is less than Y. So how do we show that this is an interval? How do we show that? So X is maybe here and this is Y. This is just R. I don't know what S is. I want to show that it is an interval. No, but S may have other points, and we want to show that S has everything in between. That right? Yeah. We want to show that S has everything in between. That is the definition of an interval, right? If there are 2 points, then there is everything in between. How do you show that there is everything in between is in S? Maybe you can write that, because that's how you'll be thinking of. Yeah, that we want to show that everything in between is also in S. You understand what in between means, in between X and Y. So once again, it's doesn't seem like it doesn't, we don't know how you can prove it directly, because what will be arrive at if you have to prove it directly, right? So assume that something is not there, something in between is not in S. So assume that there is a Z. Yeah. So how do you show that? So how do you show that? So let's say, so this is the thing, Z, there is a Z such that Z is not in S. Okay. Then we want to arrive at a contradiction. We want to arrive at contradiction. And what will the contradiction be? We basically will be arriving at S is disconnected. Yeah, seems like, right? So let's see. So there is a Z in between, which is not, so I'm drawing a very light color, Z. And exactly. How do you do that? No, don't take X open. If you take X open, okay, let's see what happens if you take, but you're almost there, okay? If you take X open, let's see. So you have to take something else, not X, but this part is correct, yeah? Just take minus infinity, simply. You can take anything less than, you can just take minus infinity to be safe, right? Because you don't know where where S extends till, isn't it? So just take till minus and just take everything. So you take everything till infinity. This is one part, and obviously the other part is Z till infinity, minus infinity. Right now, obviously, this is not, will not give you S. So you have to take the intersection of this with S and intersection of this with S. Okay, and you see, this is open, right? Obviously, it's an open interval. So if you take its intersection with S, then that is open by definition. Okay, and intuitively also, if you take any point, take an interval, that interval will be in S, you know, that interval, yeah. But let's just take it by definition. Yeah, this is open because it's an intersection of. Yeah. So this is your A and this is your B, and these are open, and the union is S. Okay, so then S is a disconnected. Yeah. So this implies S is disconnected. That's a contradiction. So simply simple, very simple. Okay. So one has to just write and just think. It's not very tricky proof, you know, but one has to understand why are we doing by contradiction and so on. So we prove this. Let's actually do the other part also. No problem. Let's the other part. So we have proved this claim that the intervals. So we have proved that intervals are connected. And we want to we have proved that anything that is connected is an interval. Okay. Now we want to show. So this is part A. What we wanted to show. Once we do this, then we would have completely described connected subsets of R in a very simple way, just that they are intervals. But obviously in R2, they are not just boxes, they are some There can be some very crazy stuff, indeed, very, very crazy stuff indeed. We will see them also. So B, what we want to show is that let, once again, these are very obvious results, but to prove them from the way the definitions are made is the challenge. Okay, let S be an interval. Now you can take any interval, open, close, whatever. I'll just take open A comma B, show S is connected. Now that's what we want to do. Show S connected. Yeah. Yes, yes, right. Once again, you have to go by contradiction, because how will you show that you cannot write? You can, that's by the very meaning of it, assume that it can be written and be a contradiction. Okay. Yes. So let's do this. That's the idea, obviously. So yeah, let's write it. So obviously, since we are new to this topic, we are doing same things when we do for compactness and such. We may not prove everything, but I'll assume that you guys prove it. So assume that S is disconnected. Let's write everything. Disconnected and S is, so I mean, that's not and, that's what it means. S is and A and B are open in S. That doesn't mean that they are open intervals, okay? They are some complicated open set in R and you have taken its intersection with S. Okay, so it's not just a simple open interval. So what do we do next? Yes, right, yeah. And that is intuitively very clear, right? That you will, if you make some open intervals, even in an R, right, and they are disjoint, you will have to skip something in between somewhere. That's what we want to prove. But how do you show that? That is the thing. What do we write to? So what is that element now? That element you cannot find so easily, but you have to describe it somehow, describe its existence. In terms of A and B, of course, that we have assumed. Yeah, just give me 2 seconds, I'll come back. Sorry. Yes. So what will that be? How would you capture that thing? So S is S is already an interval, so it's much easier. And then you have A. A is a very complicated thing, and then you have B. So this is A and this is B. How would you capture? How would you, using the language of analysis, how would you describe that point which is missing? It's just a matter of being able to describe it with the definitions. Intersection of what? S minus the intersection. No, but that is equal to, that will be empty by our assumption. Right, but that is a problem. So I can understand our assumption is wrong and we are itching to just show it somehow. How do you show that? You need more than just unions and set theory. It's like in geometry, we can see that two lines are parallel, but unless we prove it using some axiom, it doesn't. So it's just something like that, right? So that point would just be the supremum. Yeah, we would like to call the maximum, but this maximum may not exist. So it is the supremum of A or the infimum, something like that you can take, right? Supremum of A, maybe you can take. Okay. So obviously here we can assume without loss of generality that B, no, not B, B is a none of them. 1 minute. 1 second. Yeah, let's just take, let's not worry too much before the thing actually happens. When it happens, we'll have to see. But right now, just take the supremum of A. Take this, let's call this X naught. Okay, the picture is just there too, so that we don't have to read this every time. But yeah, so the claim is that the supremum is the problem. Yeah, so see, obviously here we have to assume something, that there exists a Y. So 1 minute. Supremum. Yes, but no, that's right. It should be the supremum of A, but what I was thinking may go wrong. I mean, 1 minute. Yeah, let's just take the supremum of X naught. Now, what do we do? I mean, but we want to show that the supremum of A is in S. That is what we want to show first. See, if it is outside S, then we will not get a contradiction, right? If the supremum, well, from the picture, it looks like it cannot be outside S, but then it can be, right? In general. This could be B, is what I'm trying to say. And then you would not get a contradiction, right? So just to fix, just to that, this is a minor thing which maybe people won't notice if I, in the sense that, but this is not a problem. Let's assume that this is a closed interval. Okay. Yeah, let's assume it's a closed interval for the time being. We can fix that later on about the open interval. Yeah, in that case, if you take the supremum, in that case, if you're going to take the supremum, yeah. So we would like to show that the supremum of this x naught is not in A. Yeah, so that's the first claim. Okay, claim is that x naught is not in A. Yeah, so try to prove this. Okay, try to prove that the supremum is not in A. For that, you will need to use the fact that A is open. Okay, A is open. Okay, because A is open, it will not be in A. Okay, just again work that out. Yeah, should we say that? Okay, out. 1 minute. That is something that one has to. Supremum, if the supremum happens to be in A, then A becomes like this, right? A becomes like this on this side. It's a little. Yeah, roughly speaking, you will need to use the fact that A is open. Okay, so just try to work this out. Just try to see that if A, because A is open, it will not be in A, and also more importantly, x naught is not in B. Okay, x naught will not in B, so x naught will clearly not in B in B. That is very clear. That is because these two are open. Because these two are open, the supremum is a limit point. Okay, the supremum is a limit point. So the limit point of x naught, the limit point of A, cannot be in B. That's very clear. This is clear. Okay, we need to just make sure that we prove this. So yeah, let us see where it could be a problem. So if, because A is open, if the supremum, yeah, but that doesn't contradict the fact that A is open. Or does it? So then, sorry, once again, would become like this. Yeah, let's just try to work it out. I'll also just think about this. Should be easy. Okay. Yeah, because we have to next class.